Electrical engineering is a very broad major that encompasses a lot of sub-disciplines. Within the umbrella of electrical engineering, there are fields like RF, which is basically wireless communications, where you could work on satellite communications for defense purposes so the signal cannot be jammed by an enemy. There's electronics, where you could design the circuit boards within computers or phones, or the control systems within autonomous vehicles, or the circuitry in a prosthetic arm. There's power, where you'd work with high voltage systems and delivering or generating lots of electric power. That could include working at a power plant, working with solar panels, or something like electric motors and regenerative braking, where, like in certain electric vehicles, when you take your foot off the accelerator, the motor turns into a generator due to changing speeds of certain components within the system, and then the kinetic energy of the wheels is used to generate electricity that can be stored for later use. There's controls where you'd work on things that have some sort of electrical feedback, like propulsion systems in various aircrafts, all the way to your cruise control, where your speed is monitored, then depending on what it receives, the system turns the wheels faster or slower accordingly, which then affects your speed, which is then fed back into the system, and this control loop continues. There's instrumentation, which deals with designing sensors and equipment to measure physical quantities like pressure, temperature, motion, position, and so on. You could design motion detection sensors for a security system, GPS for aircrafts, or all the sensors in your car that have to analyze fluid levels, temperatures, battery voltage, anti-skid braking system, or more advanced systems for driverless cars. These types of electrical engineers often work with controls engineers, because after all, a controls engineer could design a great system to control the speed of an aircraft, let's say. But if all the sensors cannot accurately determine the speed, air pressure, and so on, the control system is basically no good. There are many of these fields, but the last one I'll explain is signal processing. This is simply about the manipulation and analysis of signals. Signals being essentially functions that convey some sort of information. Maybe you have this sinusoidal voltage at some frequency, and then a sensor in the system causes an increase in the frequency, and that frequency change is related to the temperature that the sensor is picking up. Now that changing voltage or signal contains information about the temperature in the room that we could convert to text on a screen, let's say. But when it comes to signals in general, you might have to amplify them, like for an earpiece, or filter them where there's background noise, and much more. And this can apply to radio signals, cell phone signals, radar, missile guidance systems, speech, image, or video processing that all involve signals that need manipulation. There's GPS signals, noise-canceling headphones, and of course, way more. Okay, now I've already thrown a lot at you to encompass a lot of what you can do as an electrical engineer, and as you can see, it's very broad. It's not just one thing. As in, two people who majored in electrical engineering, as with many other engineering disciplines, could be in two totally different fields or careers and have very little knowledge about each other's work. And this is also not about being an electrician, by the way, which is a common misconception. Electrical engineering is not where you go in and install or repair electrical systems in people's houses or in offices and so on. But if you're debating picking this as a major, all the fields I discussed could seem like a lot, and you may be thinking, wait, what does an electrical engineering major look like and what can I expect? And that's what we'll go into now. While all schools are a little different, a typical electrical engineering curriculum consists of a few circuit analysis classes to just get you started, digital design, a power engineering class, continuous time signals and discrete time signals, which are what get you started with analog and digital signal processing respectively. You'll take a controls class, a communications class, which you'll learn the basics of FM and AM radio, a basic electronics class, which likely is followed by analog and digital electronics, some electromagnetism courses, which are basically physics classes, and a microprocessor class. There are some others you'll take, and this doesn't cover the math or physics classes that you'll see, but these are the big major classes to expect in undergrad. Don't worry about what they are for now, but just know this is pretty typical. Now see how regardless of who you are, you'll take some classes on most of those sub-disciplines I mentioned earlier. You got your power class, you got some signals classes, wireless communications, controls, and so on. As an undergrad, you get exposure to a lot of foundations of electrical engineering, and you become well-rounded, but you don't become an expert in really any field. That's where masters and PhDs come in, or just simply working in a field for many years, of course. You will be taking electives in the subfields you're most interested in though towards the end of college, so you will gain a little more mastery in those classes, which diversifies you and your resume from others, but it's not the bulk of your curriculum. But now let's go through these a little. The first are the circuit analysis classes. Now if you've taken physics classes in high school, maybe you've seen the basics of resistors, capacitors, and inductors. And you're going to learn how to find the voltage and current in circuits that contain these three components, first starting off with just resistors though. In the real world, circuits are normally extremely complicated, and engineers usually use software and simulations to analyze the circuit. But in school you gotta learn the basics of voltage and current in a circuit. For those who may be unfamiliar, if you imagine a network of pipes, you could use a pump that creates a pressure difference and causes water to flow around and through all the pipes. If the pipes are skinny, let's say, it'd be harder for water to flow through them. And if they're thicker, then of course it'd be easier. Well, in a circuit, the voltage from maybe a battery is like the pressure difference from the pump. The current or electron flow is like the water, and the resistors are like the pipes. High resistance is like a skinny pipe, harder for water or the current to go through. Your electronics work for many reasons, but mainly it's because electrons are flowing through the device. In school you learn techniques to find the voltage difference across various resistors, just like there'd be some pressure difference across each individual pipe. Circuits classes are a lot of systems of equations, just like you learned in school before, but more variables usually, and instead of x and y, it's usually v and I for voltage and current. And to begin, all the circuits have a constant voltage as an input, like a 9-volt battery that is not changing. Then in a second level circuit analysis class, you get into capacitors and inductors. You'll use those same circuit analysis techniques, and the voltage source will still be constant like a battery, but current and voltage in the circuit across those components change in an exponential way, like charging up a capacitor to a max voltage. In order to find that max value, or the time it takes to charge up to, let's say, half the max value, you'll use circuit techniques to find the resistance in the circuit and so on. Then you'd quickly move on to AC circuits, or alternating current, where the input voltage is no longer constant, but sinusoidal and changing over time. For these circuits, there's some more complexity added, where a capacitor or inductor in a circuit with a resistor causes the voltage to change its amplitude, but also shifts it. The capacitor or inductor can change the phase of the voltage within the circuit. The math behind this actually involves imaginary numbers. That square root of -1 you learned in high school actually has a ton of applications, and this is one. And it's not because current or voltage are imaginary, but using imaginary numbers just makes the math work when it comes to changing the phase or theta offset in a cosine or sine function. Don't worry about all that now, but it is something you will learn. There's of course plenty more in the basic circuits classes, but let's move on to the signals classes. These are essentially math classes and will be one of the most math intensive electrical engineering classes you'll take. Before this, you've dealt with constant voltages and then sinusoidal voltages, but what about, well, everything else? You could have a triangle wave, a square wave, or some really complicated and messy voltage, which is what real-world signals can be like. So what happens if you put those into a circuit? Well, in this first signals class, you'll learn something called the Fourier series and Fourier transform, something very important in physics, engineering, and applied math. This says that any function can be made up of a bunch of cosine and or sine functions added up, often an infinite amount. Here we can see just a plain square wave. But if you have a sine wave and add it to another, and then another, and you keep going, picking sine waves with the right amplitude and frequency, it will approach that square wave. In this class, you will use some calculus and some new math concepts to find those frequencies and amplitudes of the sine functions that make up some other function. So now if we put a square wave into the circuit and want to know what the voltage and current will look like, we can mathematically model it like putting in a bunch of sinusoidal waves of different amplitudes and frequencies, which you will already have under your belt. You will learn lots of mathematical techniques to simplify this for you. Now, two specific types of signals you see here that kind of look sinusoidal but not really are AM and FM radio signals, which brings us to your wireless communications course. This class is not about physics, but just more of the math behind specifically AM and FM signals. If you look at a simple AM signal, you'll notice the amplitude oscillates up and down, and if you look at an FM signal, the frequency oscillates throughout the wave. By making the signals look like this, it causes the frequencies to move up to some specific unique center frequency, like 94.1 megahertz that the radio station transmits at. This is what the station 94.1 FM is, just that station transmitting at that specific frequency. Yes, it's more complicated, but that's the general idea. Without that manipulation, you could not wirelessly send those signals for people to listen to in their cars. You'll learn why this has to be done and all the math behind that in this class. Then when you take your electromagnetism courses, it will be pretty much all physics and involve a good amount of calculus. You'll see how when you have a changing current, it creates a magnetic field around it, which then in turn creates an electric field around that, and this continues and this propagates as an electromagnetic wave, because its electric and magnetic fields are coupled together. You'll learn a lot about what those waves do when they interact with objects, like what if they hit some metal barrier, or they encounter water, how far could they penetrate if there was a receiver at some depth. You'll also learn about transmission lines, which aren't probably what you think of. The ones you learn in this class are cables that handle very high frequency signals that oscillate back and forth very quickly. You cannot just put a very high frequency signal into a normal circuit. Issues come up simply due to the laws of physics, and you'll learn about all that as well. Many of your other classes tell you about how to analyze signals and manipulate them for various purposes, but this class really teaches you about the physics of the waves so you can understand things like how a wireless signal will be affected as it travels through Earth's atmosphere when we have to communicate with a satellite, for example. Then moving on, in your electronics classes you'll finally learn about the transistor. There are billions of these in your laptop and millions in your phone to make them work. There are lots of kinds of transistors, but to simplify, in a circuit, the current often flows down here, and a little flows in here, and they combine and flow out here. You'll learn more circuit analysis techniques to analyze voltage and current in these circuits as always, but the thing is, by changing this voltage on the transistor, you can control how much current flows through the transistor, meaning the transistor can essentially act as a switch. It can allow current to flow, which is basically like the transistor being on, and it can shut off current flow, which is it being off, of course. This can create a high voltage like 5 volts and change it to a low voltage like 0 volts. This is the binary or ones and zeros that are really under the hood of your computer. You will learn about making circuits that can switch quickly and efficiently in your digital electronics class. Analog electronics is more about using transistors to amplify a voltage, which is their other main application, where amplification would of course be needed for music or hearing aids as an example. Now there are of course a few more classes I won't go into as much detail on, like in digital design you learn about logic gates, which take ones and zeros as inputs and output ones and zeros as well. The different gates output different things based on the inputs. Zooming into these is what digital electronics is, where you see the circuits that convert the high voltages to low voltages or vice versa. But in this class, it's zoomed out looking at the ones and zeros and making circuits with these logic gates. In the power class, you'll analyze electric motors and generators and do circuit analysis with those. You'll do labs where you work with much higher voltages than normal, like over 100 volts. You'll see how much power is dissipated in resistor networks and so on. And the controls class has to do mainly with systems that involve some sort of feedback. You'll look at things like stability, because if you're constantly feeding information back into your system and something goes wrong, it could continuously be maybe amplifying some output, which will lead to issues. You'll also see a lot of these graphs where you have some target output signal, and in some cases there will be overshoot, and then the signal will settle back to that target after a certain amount of time, versus just slowly charging up. You'll mathematically find that overshoot, how to minimize it or avoid it, and more. Hopefully that gives you a good overview of the major, but due to time I'm going to stop there. However, this was my major, so if you want information on specific labs you'll do from freshman to senior year of college, more specifics on the concentrations, their applications, and previous senior projects, what math classes you'll take, how my first job or internship was, and so on, they're all on this channel and I'll link some below. So if you're looking for even more depth, give those a look. Otherwise, hopefully this was a good foundation. Some schools, especially outside the US it seems like, offer majors in electronics engineering or telecommunications engineering, or some combination, but that would be for another video. This was just on electrical engineering, which encompasses lots of subdisciplines that you saw. Every school will be different of course, but you can expect most of what you saw here. And lastly, as you can see, electrical engineering can get you jobs in the aerospace field, biomedical field, at tech companies, defense companies, in the energy sector, in robotics, and so much more. But so can plenty of other engineering disciplines that are also broad. So if you're considering this major, make sure this is the type of engineering you want to do specifically when it comes to whatever field or sector you may want to go into. Otherwise, I'll end there, and if you liked the video, don't forget to comment, like, and subscribe, and I'll see you all next time.